Hello, this is Uisuyen. We are going to design the Arithmetic Logic Unit ALU, which is part of Reduced Instruction Set Architecture CPU. In this design consists of multiplexer, arithmetic unit, and also register. So we will start with the multiplexer first. This is a 1-bit 4-to-1 multiplexer, which consists of 4 inputs and also 2 control signals. Now let's do the compilation. The compilation was successful. Next, we will do the waveform simulation. So I already filled in the value. Now we will run the functional simulation. This is the waveform simulation of a 1-bit 4-to-1 multiplexer. First, we will look at the control signal. We will see this example. Both of the S0 and S1 is high, so the output selector will be I3, which is 1. And also, for this, the S1 is 0 and S0 is 1, so the output selector will be I1, which is high. Next, we will go to the 4-bit multiplexer. To create a 4-bit multiplexer, we have to create a file. Then we will insert the block to create a 4-bit 4-to-1 multiplexer. In this multiplexer will also consist of 4 inputs, and each input is 4-bit. And for the control signal, it is 2-bit. And this multiplexer will also generate one output with 4-bit. Now we will run the compilation. Next, we will do the waveform simulation. As you can see, if the control signal is 0, 0, the output selected will be I0, which is 0, 0, 1, 1. And if the control signal is 0, 1, the I1 will be selected. And if the S is 1, 0, I2 will be selected, and if 1, 1, I3 will be selected. So now we will move on to the next one, which is adder. So this is a 1-bit full adder, which consists of input A, B, and also carry input. And it will produce 2 output, which is sum and carry output. And then the waveform simulation. So in this simulation, we can see if the input is 1, 0, 0, then the carry output will be 0 and sum will be 1. If the input is 1, 1, 0, the carry input will be 1 and the sum will be 0. Next, we will move on to adder subtractor. For this ALU design, we can use a 4-bit adder and also a 4-bit subtractor. However, it will need more logic gates. So instead of subtractor, we use a 4-bit adder subtractor as the arithmetic unit. So this is the input of the adder subtractor, which it consists of 4-bit each. And this is the ALU operation code. In this circuit, when ALU OP is 0, then this will be an adder, and if it is 1, then it will be a subtractor. So to design this adder subtractor, we will insert the full adder and also the XOR gate, which connect to the input B. So first, we will look at the ALU operation code. If the ALU operation code is 0, mean it is addition, and if it is 1, mean it is subtractor. So in this simulation, we can see that if the ALU operation is 0, means 0101 plus 0010 will be 0111. And in here, the ALU OP is 1, means the input A will minus input B and get the output. So 0111 minus 0100 equal to 0011. Next, we will move to the register. So we can see this is a data register. In this register, we use the D flip-flop, which consists of clock and also active low reset signal. First, we will look at the clock. When the clock is at 0, 1, or negative edge, the output will remain unchanged. Only at the positive edge, the register will load the input and generate the output. Keep in mind that when the reset signal is activated, then the output will be reset immediately. So let's see this simulation. During the first positive edge, the input is load. So the output will be 1111. And in here, although it's not at the positive edge, but the reset signal is activated. So the output is reset, means it will be 0000. And during the second clock cycle, the output will also load the input, which is 0100. And also same at the third clock cycle, which the register will load the input. Now we will move on to the complete ALU design, which consists of two 4-bit 4-to-1 multiplexer, which is input A and input B, and the arithmetic unit, which use the adder subtractor and also the register. So in this design, we add a NOT gate at the ALU operation code. So when the ALU operation code is 1, the addition will proceed. And if the ALU operation code is 0, the subtraction will proceed. So now let's run the compilation. So we can see this is the clock signal and this is the reset signal. And this S is the control signal of the input A, and the Z is the control signal of the input B. And this is our ALU operation code. And Q will be our output. So for the first one, the reset signal is not activated, and the control signal of A is 00, means that the input A0 is selected. And for the input B, the control signal is also 00, means that the input B0 will be selected. In here, the ALU operation code is 1, means it is addition. A0 will add with B0 and we will get the answer 0111. And in here, the reset signal is activated, thus the output will be reset. And for the next one, the S is 01, thus 1110 is selected, and here 1110 is selected also. So this will add with this and we will get output of 1100. Now let's move to the subtraction part. At this clock cycle, the S is 01, thus the input A1 will be selected, and Z also 01, so the B1 input will be selected. As we can see, the ALU operation here is low, thus the input A1 will minus B1 and we will get the output 0011. Now let's see the last simulation. At this clock cycle, the input 1100 and 0001 is selected, and we can see that the ALU operation code here is still low, so 1100 will minus 0001 and the output produced is 1011. So after testing all the data given, the output produced is all comply. That's all for the video demonstration. Thank you.